Morning. So I'm Dr. P. Irvine, as you've already heard. My talk's titled Plan A+, Stratospheric Aerosol Injections Potential Role Alongside Other Climate Policies. Other people are going to give a more technical take on some of these topics, but I'm going to give you a big picture sense of what the potential is here. So I don't have enough time to go into this in much depth. This is a great figure from the United Nations Emissions Gap Report, which tallies up how different countries are doing when they compare the promises they made to cut emissions at Paris to what they're likely to deliver by 2030. The TLDR version is, if you add up all these 20 countries and you compare their promises that they made, the minimum promises they made against what they're going to do, they're more or less kind of on target to not change emissions at all. Some are going to grow, some are going to cut. The net effect is no change in emissions by 2030. This is kind of what it means. This is another plot from that UN Emissions Gap Report. In black is historical CO2 emissions or CO2 equivalent emissions. In green is what we need to do, or what we need to have started doing to be on track for 1.5 Celsius. Blue is 2 Celsius. And then orange are those minimum promises. So we're probably about there in terms of where they promised, or where they're likely to be by 2030. And so looking ahead, this goes out to 2035. I think it's pretty reasonable to expect that emissions will plateau for the next 10 years. Maybe they'll be a little higher, maybe a little lower than today. And that means we're going to not be on track for 1.5 or 2 Celsius, but more like 2.5, 3. Of course, a lot of that depends on what happens after 2035, and that's much harder to predict. So what's that going to look like? This plot here from srm360.org, all our figures are free to use, so please do. This shows sort of the policy options we have. If we just keep doing what we're doing today, never cut emissions, temperature will rise indefinitely. The amount of warming the world will receive is proportional to the total amount of CO2 we emit. So if we emit twice as much CO2, the planet will warm twice as much. Now, in purple, this shows what we will get if we eliminate CO2 emissions. We drive them to zero. And you see temperatures hit a peak, and then they stop warming. Once we've eliminated CO2 emissions, the planet will stop warming. But it will not really get cooler again. You can see here that it is slowly falling over the following centuries. Note the plot here is out to 2400 rather than ending in 2100 as normal. So you eliminate CO2 emissions, and you've got a world that is warmer for centuries to millennia. This is where, or for millennia actually, this is where carbon dioxide removal comes in. This gives us the option to accelerate the drawdown of carbon, accelerate the return to lower temperatures. But again, it's very costly. It's going to be slow. This is probably a fairly dramatic implementation of carbon dioxide removal. And even in that case, you can see here we only get out on the kind of scenario that we're on by 2350 in this kind of optimistic CDR scenario. So we are committed to a warmer world for centuries, now it seems. And that's where sunlight reflection or solar geoengineering could come in. It could help us limit warming in the meantime while these other policies are put in place. Just want to note, I'm at the Climate Systems Engineering Initiative at Chicago, and while there is a big focus there on stratospheric aerosol injection, that's not the only focus. Climate Systems Engineering is a broader concept that includes open system carbon dioxide removal, so things which modulate, like the ocean alkalinity, ocean iron fertilization, things that work in the open environment, rather than the direct air capture type interventions, and then glacier interventions to try and slow the loss of ice sheets. Just briefly, what is ocean alkalinity enhancement? There's a lot of work out there at Chicago on that. Very simply put, you add stuff to the ocean that increases the alkalinity. Increasing the alkalinity shifts the balance between CO2, dissolved CO2, and the bicarbonate and carbonate ions, meaning there's a deficit of CO2 in the oceans that pulls CO2 out of the atmosphere. And so then you have a net flow of CO2 into the ocean and you're drawing it out of the atmosphere. You're also addressing ocean acidification. There's lots of questions around this, and they're addressing sort of the whole suite of them. Is it doable? Is it safe? Is it effective? Is it verifiable? Is it acceptable? And yeah, they're approaching that from a range of things, from fundamental lab work out to potential field studies. And on the right here, I think others will go into this more detail, but these are glacier interventions aimed to slow the loss of ice sheets. John Moore's here, he can tell you more about it. But there's ideas to say pump water out from the bottom of the glacier that's lubricating it, helping it flow into the ocean. And there were proposals to put these big concrete objects in front of the ice sheet. And now I think the thinking has developed to more seabed curtains, flimsier, lighter, easier things to install that could still perhaps slow the flow of warm currents underneath the ice sheets. So that's what I'm not talking about, but just a reminder that Chicago isn't just about SAI. So SAI, stratospheric aerosol injection. What is it? My slides are slightly formatted a bit weirdly here, but I think you can get what those two words are. Here, the idea is you take high-flying aircraft, or as you might know, there's new results saying regular aircraft could do this too in the lower stratosphere, and you release particles up there. The reason the particles up there work a lot better than the particles near the surface is turbulent. So you can see here, the sun warms the surface, warm, moist air rises, and any particles that might be scattering light will get caught up in rain clouds and rained out. So aerosol particles that are very reflective, could cool the climate, only last a few days in the lower atmosphere. In the stratosphere, it's very dry, there's no clouds or very few clouds, and it's stratified. It's warmer above than it is below, which means the particles don't get mixed up, and they can loiter there for around a year or two. They spread out across the whole planet. This is not something where you can create a patch over the US and just cool that. It's a global phenomena. And you could create, by choosing where you inject, where you release the materials, you can create an even pattern of cooling. But yes, that's the idea. And you get about 50 times as much cooling if you go up there than if you release them in the lower atmosphere. But before I get into most of my talk is going to focus on the potential benefits of SAI and why we can be pretty sure of some of those. But it's worth stressing that's all else equal, and all else might not be equal. So this is an illustration of one of the key concerns of undermining emissions cuts. So here's my initial scenario. This is kind of the kind of thing we simulate in our models. There's what emissions cuts would have been, or they are, and then you add SRM, and there you go. You've got a scenario. But what if, by deploying SRM, you undermine those emissions cuts? You end up with a higher amount of CO2 in the atmosphere. That means you're going to have bigger side effects from SAI. You're going to have more ocean acidification. But that's also crucially, you're going to be committed to deploying SRM or to climate change for much longer than you would otherwise. You can see here, my plot runs out to 2400, but we need to run it out even further in this case where a relatively modest increase in CO2 emissions and a delay in CDR has happened. There's also the issue that if you were to stop deploying SAI or any other large-scale cooling intervention, you would get a rapid warming. You see it over the course of years and decades, you get this rapid warming initially, and it would tend to towards where it would have been. I think something crucial to bear in mind, though, is that there would be a day after, a week after, a month after, a year after any interruption. And if you were to restore SRM or SAI within that time period, you would have a relatively tiny bump in temperatures. It's actually, with SAI with multiple aircraft, as Wake Smith will tell you in a minute, is an inherently robust system. It's very, very many, several airports, hundreds of aircraft, and you've got a long lag between interruptions and consequences. But still, you are committed for a long, long time. And finally, broad question, whose hands on the thermostat? Who is deploying SAI and why? And what does everyone else think about it? I think one of the big concerns is, would going down this route, would it raise international tensions? Could there be war over this? These are all, the ones I've listed here, are socio-political phenomena that would all have real impacts on the world. And they can't be dismissed, though they are hard to quantify. But here I'm going to focus on that quantification, or rather a qualification of the consequences. So there is no plan B. You can't replace these other policies, so cutting emissions and carbon dioxide removal, with SRM. You would be stuck in it indefinitely. It just does not work. But would Plan A plus, so adding SRM on top of these other policies, would that be less risky than just pursuing the policies that we are today? So I'm going to be kind of asking, how do the risks of 1 Celsius of warming compare to 1 Celsius of warming offset by SAI? So somewhere like this purple blob here against that blue blob there in the 22nd century. So let's look what the IPCC said. So the last IPCC report concluded that SRM or SAI could offset some of the effects of increasing greenhouse gases, but there's ocean acidification, risks and uncertainties, etc. Is that fair? I think we can do substantially better than that subjective qualitative claim. I think we need an objective quantitative risk assessment. Because what does some mean in this case? And And so what I'm going to do here is I'm not going to give you that quantitative risk assessment. The community needs to work together. There's a lot to be done. And relatively little time before the next IPCC report, but I think it's something we should work on. What I'm going to do is talk about how warming compares to the things that SRM does not address, that SAI does not address. SAI has side effects. It impacts the ozone layer, adds to air pollution, makes the sky a little hazier. CO2 has direct effects. It changes plants. It also acidifies the oceans. And SRM would do little, or not quite nothing, but little to address those. And then there are dynamical changes. While SAI and other interventions could cool the climate, they would not address all of the dynamical effects. They produce their own shifts in weather, and the direct forcing effects from CO2 would still remain. It warms the atmosphere and sunlight cools the surface. And so that produces dynamical changes that cannot be counteracted completely. So how does warming, which we know this would be very effective at offsetting, compare to these other things? So there's a study recently, Anthony Harding et al. In PNAS, that compared the mortality impacts of heat. You can kind of guess what that word's meant to be. Heat, both extreme cold and extreme heat, against ozone and UV, which is one of the primary concerns that have been around SAI, as well as air pollution. They found that the benefits outweighed the risks 13 to 1. So the primary means by which the side effects of SAI would harm us are outweighed 13 to 1 by the difference between the extreme heat benefits and the extreme cold disbenefits of cooling the planet. And that's missing many factors. They didn't look at weather disasters, malnutrition, and vector-borne disease, but those are all driven by changes in climate. So what this says to me is that the changes in climate are much, much more important than the changes in the side effects of SAI. And so we should put more of our attention there than on those. Another fundamental, well, here I want to talk about a fundamental physical driver of change. Heat melts ice. This is something we can be very, very sure of. A warmer world is a world where there will be less ice, less permafrost. Glaciers will melt. And this is a plot by Alistair, who will give a presentation shortly going into more depth here, showing how Arctic sea ice area, the sea ice minimum, differs as a function of temperature. Now, if you're colorblind, don't worry. All the points fall on the same line. So there's a whole bunch of historical runs, future emission scenario, four different kinds of SAI and related scenarios. They're all very, very different, but the same thing happens. Arctic temperature controls Arctic sea ice. So if you cool the Arctic, you will reduce sea ice loss, and permafrost loss, and Greenland mass loss, and glacier loss. There is an element of dynamics, particularly in the marine glaciers, that's worth mentioning. I'm not going to go into much detail here, but there was a study 10 years or so ago by Ms. Cusker, which suggested stratospheric wind changes could increase upwelling around Antarctica and might melt them more quickly if you deploy SAI, despite the cooling. However, a new study by John Moore again, SAI impacts stratospheric winds. These propagate into ocean circulation changes that reduce heat flow to the Antarctic ice edge. So here the dynamics don't do anything particularly nasty. They might actually benefit us in terms of maintaining the ice sheets. Worth stressing on ice, on sea level, actually, keeping conditions at a steady level isn't going to stop sea level rise. It's going to keep the rate of change, roughly speaking, continuous. These ice sheets may already be destabilized, so keeping conditions the same might not be enough. Another one, warming intensifies hydrological extremes because warm air carries more moisture. This is a plot showing results from, I think it's some weather observations in the Netherlands, where they sorted the most intense rainfall by temperature. And you could see the purple is the most intense, and these other ones are less intense weather precipitation extremes. And you could see that the warmer the temperature is, the more extreme the rainfall is. This is a very robust physical relationship that's true across the planet. Every 1 Celsius of warming, the air holds 7% more water. And so if you were to offset the warming, you would offset this effect. And that effect intensifies in rain, storms, floods, as well as droughts, because warm, dry air passing over the land will suck up more moisture, which is why under climate change, we can see places that are getting both more intense floods and more intense droughts, because the air can just pull more moisture out and then dump more moisture out. And SAI would reverse that. I should have cast this a little more broadly, which I'll do now. Warming is a fundamental driver of biological activity. Most creatures in the world are cold-blooded, and so their internal temperatures, the speed at which all the chemical reactions occur, is determined by the environment. Obviously, they've got behavioral changes. They can live in burrows and so on. And mammals can control their temperature, but within certain bounds and with certain costs. And so what I want to stress here, warming is a very fundamental driver of the ecological impacts of climate change. Not the only one. So I wanted to look at one ecosystem that's particularly vulnerable to ocean acidification, and that's coral reefs. This is an old plot from an old paper that I was on, but it shows, see here. So this is amount of global warming along the x-axis here from the pre-industrial, where the corals were just fine. And as you go off to the right, here's RCP 8.5, very, very high emissions, very, very warm. The corals are not doing very well, indicated by the purple. And then up here, we had a whole bunch of simulations where we cooled the planet with SAI. Now, in this case, we slightly overcooled it. So returning back to the pre-industrial global mean was a little less good for the corals and doing a little less. But the main thing here is deploying SAI was substantially better than not deploying it. You can see the corals do substantially better if you avoid the warming that bleaches them. But also, even if you have higher CO2 than you would have had and then cool back to that same temperature, you can see that even at higher CO2 with lower temperatures, the corals are doing substantially better. So heat is the leading driver of coral reef damage. I'm slightly hesitant there. You can ask Daniel Harrison, but I believe, it's pretty crucial. So 2 tipping points. Warming drives most tipping points. So this is a plot, Mackay et al. 2022, just a little summary. Let me run through. Arctic sea ice, driven by temperature. Permafrost, again, because it's melting, driven by temperature. The Greenland ice sheet, surface mass balance. Extrapolar mountain glaciers, surface balance. East Antarctica, again, all driven by temperature. And again, because you're cooling the planet, you will reduce or reverse more or less effectively the full effects of climate change. Coral reefs, again, temperature is absolutely essential to wiping those out. And again, it would be very effective. Boreal forest, the shift northwards of ecosystems. Again, they're moving to temperature conditions that they're familiar with, and so they're driving northwards. Again, temperature driven. East Antarctica, West Antarctica ice sheets, I've been a little hesitant and used a slightly lighter shade of green here because there is both a surface-driven effect, but primarily it's an ocean-driven effect, and that's got a lot of dynamics in, and it's a bit tricky. But as I was saying, John Moore's paper and others suggested it could help, but maybe not completely stop the losses there. And then we have the 2 parts of the AMOC, the Atlantic-Marine returning circulation and the subpolar gyre. This is driven in large part by the freshening of the North Atlantic. You melt Greenland, you increase river flows, it gets fresher, and that slows down this current. And so by cooling the planet, you can help reverse that or eliminate that change. And then there's a couple that I'm just not sure about. The Amazon rainforest. There are rainfall changes there that might be problematic, but because you've reduced temperatures, you might be also substantially reducing impacts. And I just don't know about this West African Sahelian greening. So it's not that there's nothing left here to figure out, but that most of the things that matter that drive tipping points is driven by temperature. I'll skip over this one in the interest of time. This is some of the thinking behind this is going to Fuderman et al., which is accepted and should be published soon. You can get a copy at EGU Sphere, a review of SAI and tipping points. So one last thing, recent study from Linus Baselius and myself and Ali at Oxford Open Climate Change. The data behind this plot here, something you might not have noticed, this is a very familiar napkin diagram type plot, but the line doesn't meet at the end. It departs several decades earlier than you'd expect. Why is that? I expected it to be due to the carbon cycle feedback. So a warmer world, permafrost is melting, it adds CO2 to the atmosphere. So you've got more CO2 to remove. We found that effect, but it was very, very small compared to the ocean heat effect. Because in this warmer world, you've been pumping huge amounts of heat into the ocean for centuries. When you try to come out of overshoot, that heat in the ocean resists that. It returns back to the atmosphere. So in a case where you've kept the planet cooler for centuries, the ocean is substantially cooler than it would otherwise have been. And so returning out of overshoot is substantially easier. And it shaves, in our case, about 20% off the length of overshoot, several decades. Great. So to summarize, extreme heat is more important than SAI side effects. Heat melts ice, and that's very, very important. Warmer air carries more moisture, driving many of the fundamental hydrological impacts. Warming seems more important than ocean acidification for ecosystems, and warming drives most tipping points. And we know SAI could cool the planet and do so more or less evenly. Yeah. So, while the IPCC previously concluded SAI could offset some climate risks, I think once we do a quantitative, objective assessment of this, we will conclude SAI could offset most climate risks. However, apologies for the formatting here, that's all else equal. Those other issues I mentioned, emissions cuts, the impact on emissions cuts, termination shock, and potential geopolitical conflict are all very, very, very substantial issues and can't be glossed over. There's no plan B. Emissions cuts and CDR are still essential. International cooperation is essential. SAI would be a very long-term commitment, though it would be a shorter commitment than otherwise we'll face in a warmer world. So it's time to work on Planet Plus. Thank you very much.
So we've got 10 minutes for questions. If anyone has a question, I'll try and throw this to the audience member.
Just a comment on your last slide there, and maybe a question. Number 3 funder, U.S. government. No, that one. Number 3 funder, U.S. government. With what's happening with the new administration, do you see any changes happening there?
Yeah, there's some changes happening. I think they are not at all interested in anything to do with climate at all and are trying to destroy it everywhere. So they're just not even aware, I don't think. So I think the fact that the US is cutting funding across the board for climate stuff means that that'll probably have an impact on the philanthropic funding. There wasn't that much going on, US government funding recently on SAI. So I don't know I don't know the details, but yeah, there's a lot. The impacts are much more broad and much more focused on climate. I think they're just unaware of SRM.
Thank you. May I? What about the melting and the low-lying islands?
Yeah, so I think something. I mean, it's very crude, and I'm sure John Moore can correct me on this. If you just keep temperatures at a constant value, sea level rise will keep happening. If it's high enough to destabilize the ice sheets, you're still pumping heat into the oceans, which will make them expand. If you just keep temperatures steady, sea level rise will continue. So in the world where we just eliminate CO2 emissions, the climate doesn't go back to the way it was, and sea level rise is probably going at its fastest rate at the time that you've eliminated emissions. It's more complicated, but crudely proportional to temperature is the rate of sea level rise.
Hi, Pete. That was a great talk. 2 linked questions. One is that under a meeting under the Chatham House rule earlier this week, I heard it asserted that tipping points were the diagnosis and that SAI might then be the cure. I wondered whether I actually thought that was a terrible way of framing things. And I wondered if there were 2 other options offered at the same meeting in hushed whispers in the back. One was that ideally SAI was the prophylaxis, not the treatment for tipping points. And the second was maybe it's just the anesthesia. And I wanted to ask you your opinion on that. I also wanted to ask you a link question. Why is the tipping points community, who I hope to show your slide next week in Exeter, so incredibly resistant to the sort of message that you've just given us?
Great questions. I think so. So I was focusing there, and I think at the minute all we could do is focus on the drivers of tipping points. Once you've crossed some of them, and they are, the AMOC dynamics, if you've pushed it so far that it's starting to fall down and collapse, does going back a bit reverse it? There's a lot of work to be done there, and I don't know if we have the answers, but we know that limiting warming will limit the drivers of many of these tipping points. Some of them are more straightforward. The ice sheets, if they're melting at the top every year and you cool it and they stop melting, you've stopped the tipping point. Things like the West Antarctic ice sheet, there's all sorts of complicated dynamics underneath that may already be kicked off regardless of what's happening with the climate. So yeah, worth stressing that I was focused on the drivers of tipping points, not the reversing a tipping point. So I think, yes, prophylaxis, helping prevent this from occurring is what they can be imagined for. or most likely can be imagined for, rather than reversing a mock tip once it happens. In terms of why the tipping point community doesn't want to attend to this, great question. They had a 500-page report, which had 2 pages on SRM, citing basically citing a single comment they wrote, which said, well, because it wouldn't work once a tipping point has happened, it's too late to do SRM, so we shouldn't think about it. And no one's going to think about SRM before a tipping point because it's too controversial. Therefore, don't think about SRM and tipping points. But sort of the logic. I mean, I kind of suspect that there is an element that, they link physical tipping points with social tipping points. And I think there might be a little bit of trying to motivate society into transforming itself behind some of the reason for excluding SRM. But I'm hypothesizing.
So I have a question here. And then...
Hi, this is Frank Roach from Harvard University. I'll just comment about anesthesia briefly, that was meant as perhaps you can't do the surgery without painkillers or anesthesia, not necessarily to just be numbed. But my question for you is, when you talked about termination shock, you sort of said SRM, and then you talked about the timescales.
Mm-hmm.
But my question is, were you really just referring to SAI? Because for marine cloud brightening, the timescales of them staying there and having to respond are very different.
It's true, yes. So with SAI, you've got, I was like, oh, sorry, I got all these animations. It's not really going to be that exciting. There we go. So I think these results are for SAI. They're from Farley et al. So SAI has this sort of 1-2 year lifetime in the stratosphere. So you've got months and months before you even have a forcing or much of a forcing. MCB, they last a few days. So you turn it off and you would have a forcing suddenly. The Earth system still has a slow response time scale. I think a crude rule of thumb from a Ken Caldera paper was you get a quarter of the warming in a year, half in a decade, 3/4 in a century, roughly. So you do get a kickoff quite quickly, which is why the plot goes up very sharply. But you still got weeks, months before something really happens. SAI, you've got that extra window that the aerosols are still persisting for some time. So yeah, there's a difference there.
Thank you. I really enjoyed your talk. I'm Michael Bravo. I'm from Cambridge.
Mm-hmm.
I wanted to ask you about your model of risk.
Mm-hmm.
Because quantifying risk seems to be a good idea. I agree. But perhaps there are lessons to learn from other other kinds of hazard assessment, volcanology, for example. And what we see there is that different models of risk, different understandings of risk often produce quite different, sometimes divergent analysis of what the risks are, of things like evacuation and various kinds of volcanology response. So yeah, just a little bit of clarification about what model of risk you would choose and why you think it would produce a kind of convergent result.
Good question. I mean, as I was sort of trying to stress in this section of the presentation, I think we can quite fairly straightforwardly do this kind of dry, with the policy, without the policy, assuming all else equal. And I think, that is insufficient, but it's clear and I think essential to doing a more nuanced take where you go, well, how much do we think emissions cuts might be affected? It's very hard to say, but we should be able to explore that and say, well, what if it's 10%? What if it's 20%, 50%? At what point does it flip the sign of your benefits? So I think I don't have a very good answer, but I know this is incomplete, but I think it's an essential building block of a more nuanced analysis that takes into account these other factors. It's tricky because, a lot of these others are these unquantifiable, ineffable, but very real risks. Quantifying those other ones is tough. I mean, you could do expert surveys and so on, but it's very difficult to say. I mean, for example, how much has adaptation affected emissions cuts? People thought it would be huge. Has it done anything? Who knows? It's hard. Even after it's happened, it's hard to say what impact these kind of things had.
Pete from Otherwave in San Francisco. I have a bit of a weird question about the timeframes, the long-term timeframes, and to what extent humanity might be changing what it's doing over that time. Specifically, the rise of AI and compute eating the world. How is that going to impact all these predictions?
Yeah. Well, I think we need to worry about AI here and figure out what on earth. Yeah, so I think that's going to transform the world far more than any of this is going to do, and far sooner. And then who knows? But insofar as the world is still roughly as it is today, we've got this to deal with in the long term. If we're all uploaded to the internet by 2050, yeah, maybe we don't need to worry so much about sea level rise. I don't know. But yeah, it's tough.
Hi, Peter. Thank you for the amazing talk. Very insightful. Curious about the side effects. You reported vector-borne diseases. How stratospheric aerosol injection has any link with like vector-borne diseases in the troposphere?
Vector-borne diseases, I think, again, I think that's primarily driven by ecosystem shifts. So, if you've made... if you've made Brazil no longer suitable for mosquitoes because it's so hot that all species have left, then yeah. But I think that's primarily driven by temperature. There are, of course, hydrological changes that matter for vector-borne diseases and for ecosystems, but the temperature effects are really substantial. And I'm out of time. Thank you very much.